I'm Alyn Rockwood. I put Boulder Graphics there for want of something better. I didn't think retired looked quite as good. That was my last startup company, which was a victim of COVID. And since then, I've been happily retired doing some artwork and stuff. So quite a few years ago, Dave Hestenes, knowing that my background was in CAD/CAM computer graphics, suggested to me that I translate the terminology and technology of CAD/CAM into geometric algebra. And that sort of lurked in the recesses of my brain for a couple of decades or so. I had a hiatus from geometric algebra, and when I got the invitation to speak here, I thought, I'm going to revive that. This will be a good kick to get me back into geometric algebra. I'm going to skip the agenda. We'll get there anyway. I was getting back into the swing of things, I ran across this paper, which I really quite enjoyed. First of all, because interpolation is really one of the pillars of CAD/CAM, especially for curved surfaces. And the other is that it talks a lot about linear interpolation. That is the basis of a lot of what we do. And, you know, it raises this poor orphan of addition as an operation in conformal geometric algebra, perhaps on par with the other operations that we like in geometric algebra, rotations and reflections and all that. So I'm going to sort of carry on this tradition. Spike, who is John Hughes' lead author and probably the most popular computer graphics book. I met him and he said, I'm just finishing up the chapter in my third edition on curves and surfaces. Have you got any suggestions? And I said to him, on my final in my CAGD course, Computer Aided Geometric Design, I always ask, what is the most fundamental algorithm in computer-aided geometric design? Stephen? No. Anyway, what I was looking for was iterated linear interpolation. And a little while later, I ran into Spike and he said, I'm really upset with you. And why? He says, well, you know, after you told me about your final and went home and thought about it, I had to rewrite my whole chapter. So at the end of this talk, I'm going to ask you what the most fundamental operation in CAGD is. And I hope you'll understand why we do that. Oh yeah, extra slide. There was something in the water in 1960 Paris, or in the wine. So two major automobile companies were both very interested in, and apparently, according to some reports, independently interested in designing their products with computers. And shortly thereafter, Dassault, the major aerospace company in Paris, also started doing this thing. Pierre Bezier at Renault developed a system called Unisurf for designing of curves. At the same time, or actually about a year ahead of him, Paul de Castillo developed a curve system and a surface system for design. The difference is de Castillo, being a pure mathematician, threw his report on the shelf, probably filed it in the library somewhere. Bezier, however, was a director of new tools and advanced research. So he actually worked on implementing his ideas. I'll come back to the third point there. So Bezier took a user interface approach to his problem, designing. He wants to design cars with computers, 1960 when he started, okay. And he said, how can I reconstruct a polynomial? And cubic is a good degree to start with because it has an inflection. How can I reconstruct a polynomial so that it is something that designers, stylists can use. And he played around with these polynomials and came up with this formula, different basis function, where the coefficients, the control points, had a geometric meaning for the designer. And this is actually really a new idea. The idea of user interface driving any kind of algorithm in the 60s. I mean, some of you guys aren't this old, but computers didn't have the power to take users into concern, right? Let them figure it out. We give them the math. And so user interface, you have to give Bezier credit for this. A year earlier, DeCostajo was looking at this. How do I compute polynomials so that they are computable on a computer? And he came up with an algorithm for computing polynomials called the DeCostajo algorithm, where you input, do I have a pointer? You input the piece of i's down there on the bottom as control points, and then you calculate the polynomial.
Yeah. You can either use this or
yes, I
this
can.
as a laser.
Thank you. So you input these control points at the bottom here, and then you use linear iteration, iteratively, to compute the point on the curve. It turned out that this algorithm gave you the same function that Bezier was doing. These guys are in the same city too, right? Bezier claims it was independent. DeCostajo less so, but that's another story. At the same time in Cambridge, there was a group doing CAD-CAM using Boolean set operations. Charles Lang, being the head of this, got wind of Bezier, sent one of his students, Robin Forrest, to Paris to talk to Bezier. Robin Forrest came back to Cambridge and said, there's nothing new here. It's just Bernstein polynomials. So in the finest tradition of mathematics, the guy who invented this polynomial didn't get his name on it. Bezier did, but Bernstein, 70 years earlier, had invented the Bernstein polynomials, basis functions, in order to prove the Weierstrass theorem. Well, what is the secret? Well, the first time I saw these polynomials, these are the cubic Bernstein polynomials, I was in awe, because at any value t, if you add up the four polynomials there, it equals 1 all across that line. How did Bernstein ever come up with a set of polynomials for any degree that always add up to exactly 1? Well, there's something very powerful about that idea. You know, it's a partition of unity. And so this Bezier curve that DeCostajo came up with an algorithm, a stable algorithm for, based on Bernstein polynomials, has a lot of power. First of all, like I said, it will interpolate the endpoints. The legs of the control polygon give you the tangents. If I move those points around, the curve follows it. It's very intuitive. So it has minimal control. 4 points, the degree of the polygon or the polynomial. It has what we call variation diminishing. It's not going to wiggle any more times than the control polygon. It has a convex hull property that polynomial is always within the convex hull of this all follows, by the way, directly from the partition of unity. The linear precision, if my 4 control points are in a line, I return a line. These are all very important design characteristics. And a lot of these were proved well after Bezier. Farooqi later showed that if I convert any Bezier Bernstein form algorithm to a matrix operation, it's well conditioned. It's the best condition of all of the polynomials I can have out there as a matrix operation. It's well conditioned. DeCostajo already showed that it was the most stable. And actually Bernstein used this for his proof because it was between 0 and 1. It's always between 0 and 1 in our range. I can compute it in parallel. That systolic array that DeCostazo came up with is just a repetition of linear interpolation. So lots of nice things about this. It's subdividable. That DeCostazo algorithm actually returns to me the control points for two subdivided Bezier curves. Very important, by the way, for divide and conquer algorithms in computer graphics. It's easy to make a continuity continuous by matching control legs across two different Bezier polygons. And like I say, it's intuitive. So what happened? Oh yeah, and the surface, I'm not going to get into the details of this, but the tensor product surface of these Bezier curves, all of its boundaries are Bezier curves. It's a sweep. The Bezier curves from the internal control points, they sweep out a new set of control points that give you more Bezier curves. So it's basically just a fiber bundle of Bezier curves everywhere. So if you know the curve, you know the surface. Very nice all the way around. So Bezier, as director of new tools and advanced research, instituted a very expensive retooling of Renault to start designing automobiles. This was actually a very bold move, a lot of investment. He had to convince his stylists, who are basically artists, by the way, to start using these computer tools, that they're intuitive and everything. So everything is great. The Bezier surface, the Bezier curve are wonderful all the way around, right? So why not Bezier? We don't use it today in car design. We don't use it in very much, actually. We use it operationally. We love to operate DeCostazo. Why not? Well, okay, here's some pictures of Renaults through the years. I'll let you just look at those for a second. Can you pick out the years that Bezier's Unisurf was designing Renaults? You know that people buy cars based on how they look on curb appeal. I don't care what you think about reliability and you know, power or whatever. Car companies know you buy cars on curb appeal. So there was a period in the early 70s where Renault's brand mark took a nosedive. It became known as sort of the down market commodity car, if you wanted to buy. And the reason for that was because everything was made with Bezier patches. What was the problem? The problem wasn't in the Bezier patch. As we've seen, it really is a beautiful patch for designing a patch. It was in joining them up. The continuity conditions, once you started working all the patches around, became a Chinese puzzle. By the time you got the continuity all the way around the patch, it really constrained my Bezier patch. And so the designers ended up doing things that were very chunky looking. And that actually hurt Renault in a big way. So, you know, what's the upshot of this thing? It wasn't the patch that was the problem, it was connecting the patches. And we have since learned Bezier, B-spline, and a lot of other surface types people have come up with. It isn't the surface type, it's the connection of those surface types that really matters. So splining, the original meaning of the splines was these wooden pegs that you put between the joints. It's still a meaning. If you're a woodworker and you connect two pieces of wood with that thin spline, that's what a spline is. The car makers like to use that spline because it was bendable to actually design the profiles in that of the cars. So we kind of corrupted the use of that word. But doing a single curve or a single patch was insufficient. And in fact, we spent 10 years coming up with Unisurf and patches, but we spent 40 years learning how to put them together. It wasn't till the 2000s that a successful car design came into being, not to speak of airplane design. I mean, Dassault was also working on this, and they produced CATIA eventually out of it. So let's talk shortly about continuity. So This is something that engineers and even my math majors don't get. Physicists do because they work with particle physics. But a parametric curve has a couple of ways to look at continuity. One of the ways is, simply put, is directional continuity. I follow the tangent, the velocity vector, and if that direction doesn't change, I call that G1 continuity in the business. Now the speed can change discontinuously, but think about an automobile. I don't care so much if I'm designing whether my speed changes. I care if the direction changes. I want that smooth across there. So quite often G1 continuity is sufficient. C1 continuity, what you're used to, is both continuity of direction and speed. Now in mathematics, we can talk about reparameterizing manifolds. That's G1 continuity. If I can reparameterize the manifold to make it C1, then it's G1, right? So there's more formal definitions, but I like the direction speed idea. The inverse function theorem tells us that if we have a continuous function that is mapped by another differentiable map, then that mapping is also going to be differentiable if that mapping has full rank. Okay, so more specifically, if I am going to map my Bezier curve to say conformal space, which is, by the way, a differentiable map, then I'm going to maintain continuity as long as my derivative, as long as my Jacobian doesn't fall in rank, which it can't unless the endpoints of that polygon collapse, right? Because it's a quadratic map. So I can talk about doing a Bezier curve in Euclidean space and know if I join two of them continuously on the horosphere, it will also be continuous. But a constructive proof I think is more illuminating, pretty simple too. So, here's our conformal mapping. You should all be familiar with by now. And like everybody else does, I'm really only interested in the quadratic component of that. If I take now a piecewise linear and map that quadratically, I find that I get a quadratic Bezier curve. I don't know if you paid attention to the form, but you look at that quadratic there, trust me, that is a Bezier Bernstein polynomial, quadratic. The curve lies on the horosphere. The control points don't. The endpoints do, because they're on the curve, but the interior ones don't. More generally, if I take a general Bezier curve and I map that, I'm just going to square it, right? So here's multiplication. If I look at the endpoints of that curve, this whole thing will become, when I add it all up, I get the Bernstein polynomials. I get that basis function when I square it. This is kind of nice. When I look at just the endpoints, that's the control leg that controls the derivative, and I add them up, I get something that looks like this. When I have to strip out the Bernstein polynomial, and this becomes then the criteria for continuity on the horosphere. Does this thing from the first Bezier curve match this thing from the second Bezier curve? Well, if I want G1 continuity, all that means is that the endpoint of the one curve equals the first point of the second curve, and the difference of the polygon legs is equal. And that gives me directional continuity. If I want C1 continuity, I have to make sure that their lengths are equal. A little more constrained to get that C1 continuity. I don't always need it in design. If I look at the other coefficients, add them up, strip out the Bezier terms, I get the formula for each coefficient of the Bezier curve, which is missing. So I'll leave that as an exercise for the reader, for the student. But it's true, you can do it. So in the 80s, early 80s, Kyle Ramshaw at DEC Research, do you remember DEC? VAX and all. DEC Research Center came up with something called blossoming. And I like this idea of blossoming. And what his theorem says, what he proved is that for any degree polynomial Pn, there is a multi-affine function P with n variables such that the order of those variables does not matter. You can permute them, you get the same function. It is multi-affine. So it's linear where the coefficients are equal to 1. And if I have all of the components of that multilinear function the same, all of the variables, I get my polynomial back. So somewhere on this multi-affine function, there's kind of a diagonal going through it, which is my original polynomial. For example, here's a polynomial in T, and here in UVW, I have the blossom of that polynomial. It's a multi-affine function. You can check that out for yourself. It doesn't matter which order the UVWs come in. It's affine in each variable, right? And if I replace UVW with just U, okay, P of U equals something in T, but you got it, right? Anyway, I get my original polynomial back. It's really nice. Thing of it is we don't care. The important thing, we don't care what the blossom is. The important thing is that it exists. It's real good mathematics, right? That it exists and it's unique. And it follows these 3 principles. Because I can use these 3 principles to generate, I'm going to exaggerate here, to generate any algorithm I want on polynomials. Because I'm saying Bezier is one form of a polynomial. If I can generate it on Bezier, I can generate it for others. So this is 2 minutes. Okay, well. Or 10 minutes. Okay, let me give you an example. So I'm just arbitrarily going to say my control points are given as P0, 0, 0. That's the blossom, right? So that's a point in space. I give it. I give the point P1, 0, 0, P1, 1, 0, and P1, 1. Now remember, to find a point on the surface at value T, I have to find P of T, T, T. So I play this game. How do I go from P1, 1, 1 and P1, 1, 0 and find P1, 1, T? Well, that's an affine distance. Depending on what T is, if T is 1/2, it's going to be 1/2 of the way. This is that multi-affine property. So that's how I find P1, 1, T. Likewise, I find PTZ, okay, PT0, 0 between these two and P1, T1. Do you see where I'm headed? Then between these two, I want to get rid of I want to put another T in there. So I find PTT 0 between these two. And likewise this one. And then finally between these two, PTT1, I get the 0 and 1. I find PTT. That's my point on the surface. Yeah.
Is that accurately drawn?
I don't know. I copied and pasted.
It doesn't look very good.
In what way? Well, does it convey the concept? It's okay if you have to work a little bit to get it. Anyway, the point is, I just produced an algorithm. Which algorithm? I have linear interpolation between each control point, and I iterate on it. Which algorithm? The Castello. How do I know that the control points in this form a Bezier curve? Because I just made it with the Castello. right? So kind of sweet. I don't have to remember the Takashi algorithm anymore. I can play this game if I forget it. So all I have to do is remember this game, the Blossom method. Let's do something else. I'm gonna, probably also a bad diagram, but pay attention then. P012, I'm gonna assign a number, a polygon. P123, why did I say that? Because the order doesn't matter. Permutation, right, invariant. P234, so I'm just shifting my numbers, right? As I go up, and then finally P345. And I assign those values. And I go through this thing. Instead of looking for the value of the curve, which I could do, by the way, I'm going to look for P222, P232, P323, and P333. Why? Because those are the control points of the Bezier curve. The same curve in space that is given by these points will be given by these points in Bezier form. And I play the game. You know, where's T? There is 212. There's 232, all the elements I need. I find out if I play the game, I'm going to get these 4 points, which are the control points of the Bezier curve. I just converted from B-spline to Bezier. And if I use the T formula, played the game with T on these control points, I would produce the B-spline curve. I would reproduce the de Boer algorithm for computing B-splines. It's all there in the Blossom. So, kind of step back for a second. Let's talk about splines again. So we're going to come back to the Blossom because that's going to be our key for splining in conformal space. The Blossom exists in conformal space. There's nothing, you know, the Bezier curve exists up there. It's double the degree, but you know, it still has a Blossom. So why do we worry about splines? You know, I talked about C1, G1 spline. That's just the kind of opening the crack of Pandora's box. Okay, people worry about splining surfaces and curves together for all sorts of reasons. If I'm in the car industry, I want my reflections to be as smooth as possible. If I watch a Mercedes go down the street, and they're usually black or dark colored because they spend a lot of money and time making their reflection surfaces perfect. And you'll see the reflection just flows smoothly across that car. Unlike the car I own, which is generally more of a matte color because they don't want you looking at those reflections coming off. Okay. Fairness is a concept which is ill-defined, but everybody in the auto industry knows what it looks like. I'm talking about how do I join, see, a Bezier patch is C infinite in the interior. So how do I join them so I get these qualities in my car? Jerk, I don't know if that's an industry name or more broadly, it's third derivative. Somebody out there in fluid flow? Is it? Okay, okay. It is, okay. Very important in fluid flow. The shipbuilders believe they need C3, even though they weld these joints on, you know, but still. But if I'm a, you know, a sailboat racer, yeah, that's going to be important. Chatter. So if I'm milling, and you know, so much of your stuff is made by milling, that drill bit going across the thing, you don't want it suddenly chattering. Why does it chatter? Well, you know, it's one of the main, well, I'll get to it in a second. Torsion, I'll get to that one. Twists, this was a real problem putting Bezier things together. The twist is that basically the partial, the mixed partial, where surfaces come together. But remember, we're designing, we're defining those partials. We're not deriving them. So we have to have some way of defining those mixed partials. And people said, oh, just make everything 0, then they'll equal. Well, you could feel it, made a flat spot. So different problems with continuity. Covariant acceleration, I'm driving a car, right? Or a jet plane. You know, acceleration over a hill, I have to have. That side-to-side motion, the covariant acceleration, that's really unpleasant, whether you're in a car or a jet plane, or even on an animation curve in movies. That sudden change this way is worse than the change this way. So minimizing that between your curves. Energy efficiency is actually a big thing now. You've got robots that are moving on Bezier paths or B-spline paths, and you want them to move to minimize the energy they're burning, the electricity. So you probably never thought of those. So once again, cars are sold on curb appeal. A lot of that is reflections. Talked about jerk, chatter. So one thing that causes chatter is when you change, like you bring the ball and cutter in tighter to make a bigger fillet, or bring it back, something like that. And as you're doing that, you're suddenly engaging more metal and you get chatter. 2 minutes, okay. Torsion in our architecture, you have a supporting beam with different weights on either end, you get torsion. That beam continues. All right. Splining Bezier tubes. Okay, I'm going to hustle through this. You know that I like tubes if you've seen my art show. Work done by Dietmar, not published yet, which I was very pleased to find. Is he was looking at, given, you know, in conformal space, we can, we define points, spheres as points. So I can do Bezier curves of points in conformal space that are really splining spheres. And Dietmar looked at this problem. Several things came out of that. One is, these are 3 control spheres, and the center control sphere has to intersect the others, or they collapse. So there's some issues that come out of that. But he was looking at the radius squared. And so I thought, you know, this is nice because you've got a form here, a polynomial form for the radius squared, which is the area of your tube. But you may not be aware of it, but designing tubes is big business in this world. If you think of all the places that piping is done, and they can, you know, anything from piping in buildings to oil refineries, and they carry a lot of fluids, and having discontinuity of that cross section causes eddies. It's a problem in pipe flow. You want that continuous. So how do you produce equal radii? Dietmar worked that through. We can, you know, make a nicer user interface by scaling that one big thing. And I think it's kind of interesting to think about splining Bezier tubes. I'm not going to talk about non-splines because we don't have time. This is a talk I gave earlier. But the only thing I'm going to say about it is we can define an arbitrary genus object on a single domain. So we get rid of splines altogether. The nice thing about it is it uses a conformal map on the Poincaré disk, the hyperbolic space. Well, you guys know where I'm heading with that, right? We can couch that whole thing in geometric algebra on a hyperbolic plane. And every motion that I need to fill that plane is either a reflection or a rotation is a conformal map. Anyway, that's that's the basis function, by the way. User interfaces are an issue there. Okay, conclusion. Since 1980, really, research in CAD has been 90% on how do we spline things. I look at the research on interpolation, and there's several papers out there and surfaces, and it feels to me like we're back in Paris in 1965, okay? We're really coming up with nice ways to do the piece. My message is start thinking about splines. One way to think about splines is through the blossoms, I believe. And this morning I was sitting there listening to Leo talk, and I had this blinding flash of inspiration. Maybe we can do the blossom, because, you know, think of the blossom. It's just a bilinear twist, right? Maybe we can do that with a screw motion. And I mean, I don't know where this inspiration came from, but Leo was talking. So we have these screw motion. We'll think something, right? So we have this screw motion. If we have the inverse screw motion, so that this twisted flat, which is a bilinear, we're already in affine space. So we have this bilinear twist that matches in both directions. We really have a blossom, and it generalizes to any degree. And that was really this morning that I thought about that. So thank you.